Hello and welcome to Engineering Statics. This is Sean Boston. This is the second lecture on internal forces of structural members. Here's a little recap of what we did last time. So we looked at this simple situation of a load on a beam, and we made the analogy to an Olympic weightlifter lifting a heavy weight. And we understood that he would not only feel a force on his hands, but through his entire structural system of his muscles and bones. And when we think about the phrase lift with your legs, not with your back, that's really important. It implies that the force is felt in multiple places and that it might not always be the same in each place, and how we do things can affect how that force is supported. And that's exactly the same for a beam. A beam will not have the internal forces the same everywhere. It might be maximized at certain locations. We need to be aware of that and accommodate for that. Ultimately, in the future, after we understand how to do this, we can look at a certain member in a complex structure such as a bridge and look at all the internal forces in it and make a more informed design decision about what we need that member to look like to support all those internal forces. The trickiest thing about doing this, and we saw how to do this last time, is that previously we've been selecting the whole structure for our control volume for our free body diagram, but we're not doing that anymore. We do something a little bit more subtle. We started out the same way, but we slice through our structure at the point where we want to consider what the internal forces are like. When we go down to this, we can look in a little more detail. So if we're in static equilibrium, that means all the forces must be supported, and we ultimately saw that if we have a normal force from the pin on the left-hand side, the internal structure must be preventing this chunk of material from accelerating upwards and twisting. So when we look at that, we saw that there must be a shear force counteracting that normal force upwards. And because these two forces alone would inspire a clockwise rotation, we must also have an internal force bending moment M acting this way. Ultimately, it's the bonds of the material we have included in our control volume, and the material that's touching that right edge, the internal structure is holding itself in place. Okay, and we went through, next we described some key vocabulary, and then we also described the sign convention for identifying what's the positive direction for shear and bending moment. This can be kind of confusing at first. I highly recommend you look at this description and memorize it. This might sneak up on you a little bit. So let's take a look at a concrete example to analyze the internal forces of a structure. So here we have a beam. It's got a load of 100 newtons exactly in the center. It's supported by two ropes on either end. We know the force in each rope is 50 newtons and it's 10 meters long. And also it's in static equilibrium. What we want to find is the shear as a function of distance across the beam and the bending moment as a function of distance across the beam. We're going to measure from the left side of the beam. So something we should notice here is that we have some really specific things happening here as we walk across from the left side over, measuring our x this way in the positive direction. Right here we have a rope contacting, right here we have a load, and right here we have another rope. Those are really specific things. So these are actually going to define our boundaries that we want to evaluate the internal forces within. To do this, we're going to utilize free body diagrams, and our first one, we're going to do a free body diagram shown here in orange from between the left-hand side and before the midpoint. We're also going to do another free body diagram for control volume for the green here that's exactly at the middle point, and another one for the purple here that's past the middle point. And these are the ranges we're going to be considering. So we're going to jump in and look at the orange control volume first. And since it's in equilibrium here, we're going to say there's no acceleration either linearly or rotationally. And so if we look over here at our diagram, if we know on the left-hand side that pin provides a 50 Newton force upwards, we must have a downwards shear force over here to keep it to equilibrium. And because both of these forces acting on this alone would inspire a clockwise torque on this, or moment, we need to also have the material ensure that that is not going to start spinning. So our material actually provides a moment like this also to keep it steady. So let's go ahead and evaluate these things over here. We're going to look at the forces in the y direction and the moments also. And once again, we define, because of our criteria we described previously, downwards is going to be positive shear and counterclockwise is going to be positive. So let's jump into our force equation here. We've got a 0 equals, and we are going to walk from the left side towards the right and account for all the forces here. So 0 equals, 50 is actually upwards, so that's going to be a negative 50 by our convention here. And then the only other force we have is a positive downwards shear force. And that's it. And so therefore, V must equal 50 newtons. So we know that this is a constant, and what that means is as we go across our beam towards the right, it's going to maintain 50 newtons right there, as long as we stay in front of the 5 meter mark. So let's go over and check out our moment equation here, and I think it'll be a little more interesting. So it's in equilibrium, and we're going to go from the left side over towards the right side and account for everything that's producing a torque or a moment. And we're going to define the left side where this red dot is as our axis of rotation. And so when we do that, we're going to have 0, and then we're going to come to our moment, and it's in the positive direction by our convention. And then we're also going to have that shear force downwards, and that's going to be some distance x, because we're trying to describe how it works across this, any distance between 0 and before 5 meters. Okay? And since that is a moment that would cause the bottom of this beam to be in compression, it's defined as a negative. Now, when we solve for our moment, we find that we have this. Moment is equal to 50x. This defines a linear relationship, so if x is 0, we're going to have no moment, and it's going to keep on increasing with a slope of 50 before we get to the 5 meter mark. So we're running out of time here. We're going to continue on with the next section, but I want to show you what we're going to do next. So we're going to evaluate the green volume, and we're going to evaluate the blue free body diagram, and we're going to produce an in-depth analysis of what's happening inside the structure. So far we've seen that our shear force will be constant, but our moment will be increasing the further out we go, and that's because that this shear force is going to have a bigger and bigger moment arm the further out we go. To finish up, we're going to end up producing these graphs that describe the shear force and bending moment all the way across the beam. And lastly, we'll summarize that we just use free body diagrams, and we also have a relationship between the moment, bending moment, and the shear force. Thank you, and I'll see you next time.